All right, hello out there, and welcome to my channel. This channel is for educational purposes, and I'm not quite ready here, but here I am. Okay, and we look at usually theories of everything and go deep into them, and try to dig out what you can benefit yourself. How you can benefit yourself by learning these different theories of everything. I guess you just have to remember that it's a theory of everything. So it has wide application, even though, like in this case, it's being applied to a very narrow topic. But if you get the concepts, then you can learn to apply it to every topic. And so that's why we try to give broad coverage of, coverage of several different topics, and so you can kind of see how it applies. Today is our 460th video on the reciprocal system of theory from Dewey B. Larson. And Larson was an American engineer who lived in the 20th century. In 1959, he proposed his two fundamental postulates, just two sentences about how he believed the universe operated. And then from those postulates, he derived a theoretical universe about what the universe would look like if it operated the way he said it did. And then he wrote a few books where he compared his theoretical universe with the measured universe of the legacy scientists that they have compiled in their scientific tables, astronomical charts and scientific tables, chemistry, and so on. So today we are looking at one of his books on chemistry called Basic Properties of Matter. And this book looks at just what it says, the basic properties of matter, like the melting point and the specific heat and the compressibility. And he comes up with expressions or equations for these various properties, plugs in the atoms or compounds, and compares them with the tables. And we're looking at chapter 7 in this book called, right now, we're right in the middle of chapter 7 that's called Temperature Relations. And so he's kind of looking at the formation of the temperature scale. In Larson's system, every atom, or really every molecule, has its own temperature. And so the temperature of the aggregate is really just an average of all of the temperatures of all of the different molecules. And each molecule or atom has a heat curve, a specific heat curve that it follows. The specific heat is how much heat you have to add to something to raise it by a certain temperature. And so it's kind of like your heat efficiency. And every atom has its own specific heat curve. And they are basically quantized. And so in this chapter, he comes up with the kind of the overall curve that kind of harmonizes all of the different elements by puts it on a scale as opposed to just quantized numbers. Okay, now Larson's two postulates. The first is by far the most important. The second is just kind of window dressing. He basically is explaining how he's going about his deductive process of derivation, that he's going to use math, probability, logic, geometrical considerations in order to figure out, his process of if this, then that. From the first postulate. Okay, so the first postulate is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so that's why they call it the reciprocal system, because it is based on the reciprocal relationship between space and time that they have in motion. Now, when Larson is building his universe on motion, not matter or not energy or force, but motion. And there's a couple kind of conceptual leaps that you have to make to be able to kind of get with this idea. The first is that you have in a universe of motion, motion precedes everything else. So you have to be able to conceive of motion without anything moving. Motion precedes the thing that's moving. And then also you have to kind of be able to get rid of the idea of space and time as your background of the universe, or at least not get rid of it, but put it in the background. Space and time for thousands of years have been considered to be the container of the universe, that we are in an environment of space that's, not moving, and we are events are unfolding in time. But these are really the stage that we go through our drama, and they're kind of this passive background that we move through. But in Larson's system, space and time are the very contents of the universe. This is what the universe is made out of. The universe is made out of motion, and motion is the relationship between space and time. Basically, space and time are a fraction. Motion is a fraction, with space or time as the numerator and time or space as the denominator. And this works for something like speed. The bike is going 10 miles an hour, 10 miles of space and 1 hour of time, space over time. And that is a reciprocal relationship. If you want to double the speed, you can say the bike is going 20 miles an hour, or you can say the bike is going 10 miles per half hour. That shows a reciprocal relationship between space and time. But Larson extrapolates from that and spreads it out to all of our scientific phenomena, all matter, energy, force, pressure, electric charge. These are all forms of motion, and they all can be expressed in space and time terms only. Now, when Larson is referring to motion, he's referring specifically to a kind of motion he calls scalar motion. And a scalar motion is a more generalized kind of motion that has no direction, no specific direction. It has a magnitude, but has no specific direction. Picture a balloon that you put dots on with a magic marker. If you blow up the balloon, all the dots will be moving away from each other. The dots are moving in every direction, not any specific direction. Each dot is moving away from each other dot. And this, is not really a fictitious kind of motion. This is the motion that has been observed by all the way back to Hubble in the 1920s, who observed that all of our distant galaxies are moving away from each other. Now, that was used in order to justify the concept of the Big Bang, or I would say that was abused to use the concept to identify the concept of the Big Bang. But unless you're willing to say that our galaxy is at the center of the universe and that we are not participating in that, then you would have to accept the fact that our galaxy is also moving away from all of the other galaxies. So we are all the galaxies are basically on the surface of an expanding balloon. Now, with some caveats, the second prong of Larson's first postulate is that motion and space and time all come in 3 dimensions. So this outward motion of that balloon, what Larson calls the progression, is in 3 dimensions. And if you suck in the balloon and move it inward, that is what Larson refers to as gravitation. So this outward movement is really the source of everything. Everything comes from that outward movement, which is omnipresent and eternal. It is occurring at all times, in all places. This expansion. That is the source. That motion is the source, but it has to be harnessed by reversing it and turning it into an inward motion, which is done first with the photon. The photon basically reverses it in one or the other of space or time, so that the thing is progressing. This brings in this discrete unit postulate. Space and time come only in discrete units, as does motion. One unit, and the progression goes 1 unit of space per 1 unit of time, and that's the speed of the progression everywhere in the universe at all times. It's constant. 1 unit of space per 1 unit of time. And the photon basically reverses the progression in either space or time. So it continues to progress. Say it reverses it in time, it continues to progress in space, but now it is basically oscillating in time, so that it is not moving. It's stationary from a stationary viewpoint in time, but it is still progressing in space. And that accounts for the wave-like motion of the photon. And there's some dispute among Larson's associates whether that is really how the photon got started, or whether it's from more of a combining 2 different rotational motions. But regardless, the idea is that it is a sine wave and a simple harmonic motion, and that it is the building block where you start. Once you have the photon, then you can start rotating that photon backwards and overcoming the progression. So you have to rotate it in 3 dimensions, which is done with two-dimensional rotations. And then there can also be a 1-dimensional rotation in the opposite direction, which is more like filling in the spaces on the periodic table. So Larson's periodic table, every element contains 3 numbers. The first is a primary 2-dimensional rotation. The second is a secondary 2-dimensional rotation. They alternate, first one, then the other, then the other, then the other. And then this optional 1-dimensional reverse rotation, which is 0 in the noble gases. And then it's positive in the electropositives and negative in the electronegatives. So a lot of things boil down to the reference point. So when you have this progression outward at 1 unit of space in 1 unit of time, every unit of time, at all locations in space, this this one unit of that's 1 unit of speed. 1 unit of space and 1 unit of time is speed. That is also known as the speed of light. So this progression is occurring at the speed of light, outward in all directions at all times in all places. And that is what Larson calls the progression of the natural reference system. So Larson has a natural reference system, which is moving, a moving reference system that he says that's what the universe operates upon. That's where the universe makes its measurements from that progression of the natural reference system. But us humans, we use what he calls a spatial reference system. And this is really your container universe. This is your 3 dimensions of space in a still frame, XYZ coordinates, and time is progressing. Time is always getting later and later and later. So this is the result of establishing a gravitational system. So once you've rolled back that photon enough times, and once that mass becomes a big enough aggregate, then you basically establish this spatial reference system. You can do it abstractly if you take one of the dots on your balloon and you assign it as a reference point, and you basically arbitrarily say that this particular dot is motionless. And then you'll be able to perceive that all of the other dots will be attracted by that first dot, or if it's an outward motion, then repelled by this first dot. It will look as if there's a force field there, but there isn't. Every dot is pursuing its own course, and so that is what Larson calls an as-if force. And so you have this spatial reference system, 3 dimensions of space, coordinate space, and clock time. The time is still scalar. The space is stationary. But you also have a realm of the universe, and we are accustomed to that. That's our normal environment. But in another environment, by the reciprocal postulate, we would also have 3 dimensions of time in a still frame and progressing space. Space will always be getting farther and farther and farther apart. That occurs in what Larson calls the cosmic sector. And the difference there is the speed of light boundary. There's a speed of light boundary, the speed of the progression, that is the midpoint of the universe, or the 0 point. And so the reference point, the natural reference point. And half the universe is moving slower than that. It calls that the material sector, and that's where you have your coordinate space and clock time. And half of it is moving faster than that. And that's where you have your cosmic sector, and you have cosmic atoms and cosmic molecules, and you have coordinate time and clock space. Cosmic atoms and molecules, or none of this cosmic sector, has really been identified by the legacy scientists. They've noted some of these things, but they don't understand their origin or their meaning. They call a lot of them antimatter or mesons. These 2 sectors are reciprocals of one another. So this gives the reciprocal system a great deal of power, because what we observe in our sector of the universe, we can extrapolate it over to the cosmic sector. So even though we don't have a good glimpse of the cosmic sector, we can tell it exactly what's in it, at least on a general level. Not down to the individuals, but on a general level. Okay, then we also have a boundary within both the material and cosmic sectors, where you have the unit of time in the cosmic sector and the unit of space in the material sector, where if you don't have a full unit, you don't have space in the material sector. And so if 2 atoms approach each other to 1 unit, they can't get any closer, because there is no such thing. And so instead of continuing to move closer in space, they actually move farther apart in time. Because time is the reciprocal of space, so moving outward in time is the equivalent of moving inward in space. Larson calls this the time region. In the cosmic sector, he calls it the space region, and that's where they move close. The cosmic atoms move so close together in time that they can't move in time anymore, and they have to move in space. And so, and also when you cross that boundary, the rules invert, and now the progression is moving inward in equivalent space, and gravitation is moving outward. And this creates an interatomic equilibrium, because the progression is constant and omnipresent and eternal, whereas gravitation is based on an inverse square law. And so there is a point at which they become equal, and that's where the interatomic equilibrium is established, and that's what's known as the interatomic distance. But Larson doesn't believe in the nucleus of the atom. The atom is one thing. It's a combination of motions. It's not a combination of particles. It's just one thing that can be given many different kinds of motion, like a curveball. You know, a curveball is moving through space, but it's also spinning, maybe even in more than one dimension. Okay, so, you know, the atom doesn't have a nucleus. It's just an atom. And so the sizes of the atoms in legacy science are much bigger than they are for Larson. For Larson, the nucleus is really the entire atom, and the distance between the atoms is much larger in Larson's system. That is their, you know, their geometrical bonding. Okay, let's get into this temperature relations and see if we can pick up a few breadcrumbs and maybe make a few connections. A lot of this will probably be foreign to most people who don't know the basic concepts. There's so many different concepts that you have to be able to pick up on the reciprocal system. But the thing is that it's much simpler than regular science and or liberal arts and everything, because once you figure out how the concepts work, you can apply them to every subject. So you don't have to learn a whole new nomenclature and conceptual map for every subject. You just learn one, and then you can figure out how to make it apply to the others. Larson has books on economics. He's got a book on metaphysics that has chapters on religion and philosophy, ethics, free will, memory, you know, a lot of psychology in there, dream interpretation, you know. So Larson attempts to apply his subject, his reciprocal system to many, many, many subjects. And when you can see that he does that, you can try to figure out how to apply it to your subject, whatever it is that you're passionate about. Okay, but right here he's talking about temperature relations within chemistry. It might be expected that this would result in a net effective specific heat of 8/9 of a unit, or 2.2 R. Here he's talking about the specific heat at the transition point instead of the 7/9 unit, 2 1/3 R, that exists when the initial negative level is 2/9 of a unit. Here we're talking about a solid specific heat curve. Now the solid does everything that it possibly can to avoid becoming a liquid. And so it uses these machinations of switching to a second rotational level so that the slope of the specific heat curve is reduced by a factor of 8. This was covered in the last couple chapters that we went through here. But the basic idea is that Larson derives this from probability. It's more probable to be in a low energy condition in this sector of the universe than a high energy condition, and so the atom or molecule is going to want to stay in the solid state as long as possible and is going to do everything that it possibly can to avoid transitioning into a liquid. But it is quite clear from the measured specific heat values that this is not true. The first transition point in the specific heat curves, the specific heat curves have several different transition points or inflection points where the slope changes, either as a result of a first order transition, which is a change of the actual geometrical structure of the atomic grouping, or as a result of it picking up this changing to a second rotational unit for the heat, because when you are in this interatomic equilibrium, you're beset with two different major factors. Again, the progression and gravitation. The progression is moving inward, and so this manifests as internal pressure or compression. And then there's an outward movement, which corresponds to gravitation, which is also heat. And so those are the two forces that the time region, the two major forces that the time region or the solid state has to negotiate. And it does it through these various transitions. The first transition point in the specific heat curves of the electromagnetic elements is 2 1/3 R, just as it is in the curves with the 2/9 unit. And the 2/9 unit comes from the two photons that are at the center. There's one photon, and that combines with a second photon, usually when two subatomic particles combine, and then they combine photons. So all atoms have two photons in them, whereas the subatomic particles have one photon. And so this 2/9 unit refers to two photons. A 1/9 unit would refer to one photon. And this comes into play where we're talking about something like called the interregional ratio, which is really what it's a fraction that you have to reduce your observation by, because it's the amount that you lose in the translation when you are viewing into a different sector or a different region of the universe, where you're looking into the time region. You have to reduce things by the interatomic distance. I'm sorry, by the interregional ratio. Apparently, so again, this is all extremely complicated, but again, compared to legacy science, it's very simple. Just think, you didn't complain when, well, maybe you did, but when you were learning legacy science when you were in high school, you weren't like, this is so complicated, because they were shoving it down your throat and you had to learn it. But now this is really complicated, but you only have to learn it once. You don't have to learn it for every subject. And so the payoff is huge if you actually can become fluent in this stuff. Okay, apparently the restriction that prevents the existence of the more negative initial level in the specific heat of these elements is gradually eliminated as the temperature rises, so that at the transition point, the effective negative component of the specific heat is the normal 2/9 unit. The thermal factors of the higher inert gases, krypton and xenon, which have no rotation in the electric dimension, are 100 rather than 111. And these factors are somewhat related to the three factors that Larson uses for his periodic table for every element. As incompressibility, this is a peculiarity of the mathematics and has no physical significance. In both cases, the meaning of the symbols is that the effective magnitude is determined entirely by the factors A and Z. in multiplication, this requires a unit value in the y position, whereas in addition, the 0 is required for the same purpose. Now, the main thing that you just kind of have to know about this is when he's figuring out the compression, he uses these three numbers, a slightly modified version of these three numbers, and he multiplies them together. And that kind of determines the factors that he uses in his compression equation. But when he's figuring out temperature, he takes those three numbers, often the same numbers, and he adds them together. Okay, normally the adding together is kind of that's really more of a scalar thing, where you can't multiply scalar dimensions. I didn't mention it earlier, but when you have this coordinate space and clock time, or coordinate time and clock space, you have this 3 dimensions of space. Well, it only requires 1 dimension of motion, 1 dimension of scalar motion, to account for 3 dimensions of space. But there are 3 dimensions of motion as well as space and time. So no reference system, no stationary reference system can account for 3 dimensions of scalar motion. And so the scalar motions are independent of each other. And so that's why you have to add them together as opposed to multiplying them together. And so the compressibility numbers are much more like multiplying the dimensions, whereas the temperature numbers are much more like scalar dimensions that you're adding together. Okay, just I guess I don't really have time to continue here. I don't even think I read a whole paragraph. This is an incredibly long paragraph, by the way. Larson is a great writer, but he's a terrible teacher. And he died back in 1990. And I'm not complaining about it, because you take what you can get, and it's incredible work that he did. And he didn't know all the different factors that he was facing. He was writing for more of a scientific audience, where in hindsight he might have written for more of a lay audience, once he recognized that the scientific audiences were not really receptive to anything that went against what they already, had already invested their time and energy into learning. But as a result, he gets out into the weeds like he is here, where he's just talking about something that if you're not a master of the reciprocal system, none of this really means that much to you. Anyway, thanks for tuning in.